Welcome to repeated real roots in theory. So recall, if the differential equation ay double prime plus by prime plus cy equals 0 has characteristic equation ar squared plus br plus c equals 0 with repeated roots, repeated real root, R1 equals R2. We'll set that equal to alpha. Then we get the solution y1 is equal to e to the alpha times t. Again, we need two solutions to form a fundamental set. So what can we use as our other solution in the fundamental set? So let's go ahead and consider the differential equation y double prime minus 2 alpha y prime plus alpha squared y equals 0. This is the standard second order differential equation with repeated characteristic equation with repeated real root alpha. So note, if we do the characteristic equation, we are looking at r squared minus 2 alpha r plus alpha squared equals 0. That left-hand side factors as r minus alpha squared equals 0. And so we get r1 equals r2, both equaling alpha. So what this means is we have y1 is equal to e to the alpha t. Now we're going to find y2. We're going to use a trick that looks very similar to variation of parameters. And it's actually called reduction of order. So we're going to assume that y2 is u times y1 for some function u of t. Oops, that's not a u, for some function u of t. So we have y2 is equal to u times e to the alpha t. Then we're going to plug y2 into y double prime minus 2 alpha y prime plus alpha squared y equals 0. So we have y2 is u e to the alpha t. Then y2 prime would be u prime times e to the alpha t plus alpha times u e to the alpha t. Again, that's using product rule. Using product rule again to get the second derivative, we wind up getting u double prime e to the alpha t plus 2 alpha u prime e to the alpha t plus alpha squared u e to the alpha t. So if we plug this into that differential equation, we would have y double prime. So u double prime e to the alpha t plus 2 alpha u prime e to the alpha t plus alpha squared u e to the alpha t minus 2 alpha times u prime e to the alpha t plus alpha u e to the alpha t, and then plus alpha squared times y2, so times u e to the alpha t. This all has to be equal to 0 based off of our differential equation. So this becomes, if we simplify, we have u double prime e to the alpha t plus 2 alpha u prime e to the alpha t minus 2 alpha u prime e to the alpha t plus alpha squared u e to the alpha t minus 2 alpha squared u e to the alpha t plus alpha squared u e to the alpha t. And this whole thing is set equal to 0. These two plus 2 alpha u prime e to the alpha t minus 2 alpha u prime e to the alpha t cancel each other out. And then plus alpha squared u e to the alpha t minus 2 alpha squared u e to the alpha t plus alpha squared u e to the alpha t cancel each other out. And we wind up getting u double prime e to the alpha t is equal to 0. E to the alpha t is never equal to 0. So this gives us that u double prime must equal 0. From here we get that u prime shall be the integral of 0 dt. I'm going to give myself a little more room. U prime is the integral of 0 dt, and therefore u prime is just a constant c. We can pick u prime equal to 1. We are only looking for one additional solution, so we just need one y. That's not just 0. From here, we therefore get that u is equal to the integral of 1 dt. And this is therefore t plus c. And we will go ahead and pick u equals t. Then we have that our y2 was u times y1. And so we get y2 is t e to the alpha t. So our question now is, do our y1 and y2 form a fundamental set of solutions? So our y1 was e to the alpha t. Our y2 is t e to the alpha t. y1 prime is therefore alpha e to the alpha t. y2 prime, again, we have a product rule. We have y2 prime is equal to e to the alpha t plus alpha t e to the alpha t. So now we want to find the Wronskian. So the Wronskian of y1, y2, we do y1 times y2 prime minus y1 prime times y2. So we are looking at e to the alpha t times e to the alpha t plus alpha t e to the alpha t minus alpha e to the alpha t times t e to the alpha t. If we do our distribution and multiplication, this becomes e to the 2 alpha t plus alpha t e to the 2 alpha t minus alpha t e to the 2 alpha t. Those last two terms cancel out, and we are just left with e to the 2 alpha t. This again is non-zero. And so we have that our Wronskian of y1, y2 does not equal 0. And therefore we get that y1 equals e to the alpha t, and y2 equals t e to the alpha t, form a fundamental set of solutions. In the next video, we'll put this trick into practice.